to give you some early history, people that were important along the way, and then you guys can get these down in your notes and fly by it, and then we'll get down to doing some real practice on some of this stuff in class. So we'll make better use of our time. So just as we go, don't be afraid to pause, rewind, and things like that in order to get these in your notes. All right, way back when, there was a guy named Democritus, and this is like way long ago. And Democritus came up with the idea of an atom. He was the one who said, there's this tiny, invisible, indivisible thing that all matter is made up of called an atom. He kind of thought of the concept. And because of him, that's why we call it an atom or an atom. And he couldn't prove it. He wasn't doing real science. He just came up with the idea. No one can prove him wrong. He said they're invisible and indivisible, and you can't see them or measure them. And so people are like, oh, okay, whatever. It wasn't really until the 1500s, somewhere in there, that we start to see actual chemistry taking place. And it wasn't because of a love of science. George Bauer, in the 1500s, wanted to make money, right? And so when you dig up rock out of the ground and you have this ore, so it could be iron ore or aluminum ore, which is called bauxite. But the idea is, how do you get the metal from that ore? And if you can get the metal from the ore, then you can sell it, then you can make money. So an awful lot of refining and smelting and things like that went into it. And he did a lot of good chemistry because he was trying to find a way to make more money. This guy has the best name ever. Philippus Theophrastus Bombastus von Hohenheim. He was looking into the idea, and this is in the 1500s, which is a pretty big deal, that your body can be affected by the food that you eat and the minerals and things that you get. He didn't know about vitamins. He didn't know about certain minerals that you might need. But he was trying to treat his patients, not like a doctor today, but a doctor way back then, treat his patients with certain minerals that maybe they had deficiencies of iron, or maybe they had deficiencies of potassium or whatever. And he found that sometimes giving people clay to eat or bits of metal to suck on, those kinds of things, helped his patients. And so he kind of advanced the idea of we need certain elements in our body, certain metals especially, that he called minerals. There's this guy named Berzelius. I love his picture. Look at that picture. That's awesome. Anyway, back in a long time ago, there was the leftovers of the Middle Ages were all of those symbols that you see over on the right, where they were used like a special shorthand, like a secret code, because people had been trying to turn elements into gold. And so they would write down their recipes in this secret code. Berzelius was like, you know what? I don't really want to think about the whole earth right here, like this one right here. I don't want to think of earth or gold or tin as having those goofy symbols. I would much rather have maybe a symbol like AU, which doesn't make any sense to us, but it's from the Latin word for gold, aurum, and so AU actually meant gold. So he went a long way towards creating symbols that actually had some meaning. And you can look at these and go, wow, some of these are really messed up. Just imagine having to write that for sulfur down there instead of S. It would make it much worse. So there's some things up here that we don't really use anymore. Aqua regia is a mixture of two acids, and quicklime is calcium oxide and some other things. But he's the one that came up and said, yeah, these symbols aren't working. Let's find something else. So George Stahl, this guy, he was someone in science history, but he was not very good at it. He postulated that there is this thing called phlogiston in all material that burns. And so when you burn something, you are using up the phlogiston. There's also phlogiston in the air. And so that when you're burning something, you're using up all the phlogiston. And when does a fire go out? Well, the fire goes out when all the phlogiston is gone. He said it's invisible. He says it's nothing that you can weigh or anything like that. It's kind of just like this secret thing. So if you put a candle inside of a jar and put the top on it, the candle goes out. And why? And he said, aha, I know why. Because it is dephlogisticated air, meaning all the phlogiston has been removed. Okay? So if I were to stick a bag over your head and clamp it around your neck, you would stop breathing. You know why? Because the air has been dephlogisticated. I know that sounds silly to you, but back then he came up with that and people were like, oh, of course, there's this thing called phlogiston. Antoine Lavoisier said, I don't think so. And he was able to prove actually the idea that oxygen is the thing that supports combustion, that oxygen is what we breathe. Okay, so he was able to prove that it is something you can prove and it's not phlogiston. He also came up with LOCOM. LOCOM means law of conservation of mass, meaning however much mass goes into a chemical reaction, the same amount of mass has to come out. And that was something Stahl had said. He said you can't weigh phlogiston. But Lavoisier was one who was able to say, you know what, if you have 15 grams worth of reactants go in, things that react, then you ought to have 15 grams worth of products come out, because that's the way nature works. It's a law, remember, so all we have to do is state what happens. Joseph Proust in the 1700s knew the law of definite proportions, and the law of definite proportions is just this. The law of definite proportions is the idea that it doesn't matter what you have, that things always occur in a definite proportion. So if you have water, let's draw some water up there. Water is always 2 hydrogens and an oxygen, always. That's what it always occurs in that definite proportion. All the water molecules are going to look the same. Same thing with a cookie. Let's take an Oreo cookie. I know it's red, but so well. There is a crispy chocolate wafer, and here is another crispy chocolate wafer. And what goes in the middle of an Oreo? Delicious, creamy filling. Now, what is the ratio? 2 crispy chocolate wafers to 1 creamy white middle. And that's true for every Oreo on the planet. Every regular Oreo. Not the double stuff, not the broken ones. Every regular Oreo has that ratio. The law of definite proportions, meaning that every chemical compound exists in a certain ratio. A little bit more history. Dalton, his name was John Dalton. He was actually a minister's son, and he had a fondness for the world around him, and so he just spent some time coming up with different things. He did develop something called the atomic theory, but more importantly, he came up with the law of multiple proportions. Okay, and the law of multiple proportions was really important because the law of multiple proportions says, basically, that H2O is one chemical compound and H2O2 is a different chemical compounds. So as long as things occur in a simple whole number ratio, then you can have multiple compounds. All right, so that's water. This is hydrogen peroxide. This puts out fires. This, in its purified form, is what we put in liquid-fueled rockets. And so this one would actually create more fire, and this one would actually put out a fire. So 2 totally different compounds. By the same token, you can have carbon monoxide and carbon dioxide. And they occur in a multiple, so it's like 1 to 2. It's never like CO 1.5 because you can't split an atom. And CO to CO2, this one will kill you. That one right there is bad for you. This one, I mean, if you had too much of it, it would kill you. But this one in low concentrations will kill you. This one right here, you breathe out, you actually make. So there's quite a bit of difference. And if we go back to Oreos, Oreos is a very general class. You can have double stuff, you can have single stuff, or you can really have like a quadruple stuff, right? Because you can take 4 of them. I mean, 2 double stuffs and put them together. I'm sure y'all have done that at home. But it always occurs in a whole number ratio. 2 crispy chocolate wafers to 1 creamy white middle, 2 crispy chocolate wafers to 2 creamy white metals, 2 crispy chocolate wafers to 4 creamy white metals. Always a whole number ratio between there. It's never like 1.37. Okay, and that was the magic of Dalton's law of multiple proportions. All right, Dalton's atomic theory was the same thing you've already found in your guided reading, and his basically said, everything's made of atoms and all that kind of stuff that you guys already have down in your notes. Thompson in 1900. This was kind of a brand new age because now we had electricity and stuff. So he actually discovered the electrons using these things called CRT tubes. CRT tube stands for cathode ray tube. And of course it uses glowy stuff, right? So that's him down there looking very serious. So here's Thompson. His friends called him JJ, but here's Thompson's thing going on. And you can see here is a tube which has most all of the gas taken out. There's very little gas in there. And this is hooked up to an electric source. So it's like 5,000 volts, a lot of voltage. And when you run that much voltage to it, a light turned on in there. Now, he couldn't tell which end the light came from, but he knew that there was light in there, and he would soon discover that it was electrons. This is what one of the tubes actually looks like, this glowy light inside. He found that by using an electromagnet and a magnetic field and electrical field, you could actually steer this beam of electrons. So you could make this electron be attracted to this plate or pushed away from this plate. And this was his first sense that, wow, this end's positive and this end's negative. So they must be attracted to the positive end and pushed away from the negative end. And so maybe the particles that are in there, which he would call electrons, maybe those particles have a negative charge. And there's one in real life. He threw a magnet in there and saw what happened. He put a paddle wheel in here. So he puts a paddle wheel in this thing. So right in here, he put a paddle wheel on our set of rails. And what happened was that paddle wheel actually spun. And when that paddle wheel spun, it proved that they had mass. And he was like, oh, that's awesome. He also put things in there like a cross or a disc with a bunch of holes in it, like a metal disc with a bunch of holes in it. And he saw, which way were the shadows going? Was the shadow on one side or the other? And using all that, he was able to figure out this thing right here, which I'll let you read for yourself. The light actually starts out over here, okay? And here's a cross, which I'm sure you can see if you stare hard enough. And then the shadow is way back here. So he knew that this was the negative end, and they were being attracted down here to the positive end. Okay, because you can see the light casting a shadow. This movie right here is kind of cool. This movie is, look at the beautiful colors. People used to line up in tents in the early 1900s to watch this. They'd pay 5 cents and they'd go in and they'd watch this. And then after a couple minutes, they had to leave because it was the next person's turn. This is called a Crookes flower tube. Not because they were robbing people, but because that's the guy's name. This is what it actually looks like. And you can tell here, see the Crookes flower tube? Those are those flowers. And notice those flowers don't have any color, but here they do. And notice there's a shadow being cast every so often. Well, that shadow being cast is from this. So the electrons would come down from here. They would hit this vein. It would spin that vein around, and that's what cast the shadow. But when those electrons hit this, turns out all these flowers are coated with a different phosphor or different coating that gives off light. So when the electrons hit it, they each give off a different kind of light. The bad news was that it also gave off a lot of X-rays, which no one could see. But we know now that that's not a good thing and can give you cancer and things. But back then, they didn't know. All right, Millikan, trust me, we are coming to an end. Millikan was the guy who came up with this concept of, let me measure the mass of an electron. So he found the charge and mass of an electron. If you ever want to do some study and see what he did, his experiment called the Millikan oil drop experiment was actually quite ingenious. So if you want to look that up, it'll give you something to do. You don't have to, but just in case you want to. All right. An electron weighs diddly squat. That's what he found, basically. So since he knows the electron weighs diddly squat, then we know that all the mass in an atom has to come from the other things, from the protons and the neutrons.